All right. Now, today we're going to start a topic that is not in the book at all. So probably behoove you to take some good notes, or I guess you can always, now they're videotaping this, you can always refer to those. But anyway, at any rate, in the same way that we had section P for the program material, you know, the theory of programs, we have this next section I've labeled G, and the topic is growth of functions. So none of this material is in the book at all, but it's a very important topic. Whenever you do data structures next year, we'll be using this material all the time, and so we're going to include it in this discrete structures. Now, so let's begin. Maybe we could close that door. We can begin. Let me begin by asking you a question. This is asymptotic notation. Now, you know that whenever you run a program, or whenever you buy a program from a company and you run it, how do you want those programs to execute when you execute the programs? Obviously, well, correct. Oh, that's a good point. First of all, you want them to run correctly. Yeah, if they don't run correctly, if there's mistakes in the program, then that's bad. But assuming that they run correctly, how do you want them to run? Fast. You want them to run fast. So the question, and that's the speed of how fast programs execute. That's the application of this material. So suppose that you write a program and you use one algorithm. Let's call it algorithm A. That's an R. It's algorithm A. And suppose you run it and you have a stopwatch or something and you run it, and suppose that the time that it takes this program to run is 15n plus 93. All right? Now, and what we mean by n here is the number of data. Say that it's some statistics program, or maybe it's a map, maybe and n is the number of cities on the map, and you're doing some computation for a map, or maybe maybe it's a statistics program and n is the number of data points that you're analyzing. Okay, so and you notice that whenever so this n is some measure of the size of the problem, and you notice that, like, if you're analyzing, like, say 1,000 data points, so if n is 1,000, and you time it, it takes 15 times 1,000 plus 93 units of time, milliseconds, microseconds, whatever, years, Okay, so and suppose that you notice that it runs like this. This is how it runs. And then let's suppose that you have another algorithm, or you write the program again using a different algorithm. And so now this one is algorithm B. And suppose that algorithm B, you measure it, and you see that the way it grows with the size of the problem, it follows this relation, 2n squared plus 1. All right? Now, so you see what we mean up here on our chart. This whole thing is called growth of functions. So now this is what we mean by the growth of functions. What we mean is, if n is, for example, the number of data points that you're analyzing with these algorithms, what we mean is how much longer does it take to run the program if you increase the number of data points that you process. All right, that's what we mean by the growth of functions. And I'm giving you this hypothetical. Suppose algorithm A, the time it takes to run this program is 15n plus 93. You have algorithm B, the time it takes is 2n squared plus 1. Okay, so here's the question. Which is faster?
Well, it depends on how big the n is.
Yeah, a little bit of a trick question. It does depend. The answer is it kind of depends. So in order to investigate that, let's graph these. Okay, so what we have here. So this is time. This is the time axis, and this is the n axis. And so if we graph time versus n, what kind of a curve does this look like? What's the intercept of?
Linear. It's 93.
Yeah, if n is 0, the y-intercept is at 93, right? So this starts up here at 93, okay? And it's linear, so and the slope is 15, so depending on the scale, whatever, okay? This is going to look like this, right? So here, let's just label this. This is t sub a. This is the time, the graph for the time. And what about the y-intercept for this? 1. So this is going to start right down here. But on the other hand, you know that this n squared makes it look kind of like a what? It's like a parabolic. So it's not going to be linear. It's going to go. So there's going to be a point. There's going to be a point at which what happens?
B is.
Yeah. So the answer. Okay. So here we go. Boom, 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 boom. And this point right here is known as the crossover point. Okay. So this is the crossover point.
Do we have to calculate that?
Well, I mean, you could if you wanted to. You'd set this. It's where these two are equal. So you'd set this equal to this and solve for n. Quadratic equation, right? So you could calculate that where that is if you wanted. Well, we're not going to, but anyway. The point of the crossover point is that less than the crossover point, algorithm B is better. If n, okay, so if n is less than the crossover point, B is better, but if n is greater than the crossover point, A is better. All right. But now, you guys, which one is the most important region? Are you really interested in an algorithm that works really, really well for small numbers of data? Normally, our programs are used to solve big problems. The bigger the problem, the more we want to, use the computer to solve it, right? So even though it's a little bit of a trick question, you can say, well, it depends. But actually, A is better, even though it's worse for small n. Okay. So the way we say this, is like this: for sufficiently large n, A is faster. All right. Now, you see what we set up here? Asymptotic notation. Well, what we mean when we talk about asymptotically, which one is better, we mean for very large values of n. All right, and so we could have several crossover points here. If these things are, cubic or something, and they have dips or whatever, and there could be whatever. But what we mean is asymptotically for very, very large values of it, which one is better. And one little thing that we learned here is that even though this is a 15 and this is a 2, and 15 is greater than 2, still what's going to happen is for sufficiently large n, this one's going to whoop, overcome this one, and this one is still, and even though this is 93 and this is 1, still it's not as important that 93 is so much bigger than 1. It's that this one is n and this one is n squared. Are you with me? In the long run, the multiplicative, so this is a multiplicative constant and this is an additive constant, okay? So one thing that we can note here is that at least in this particular case, in the long run, the multiplicative constants and the additive constants do not matter. Okay? So now, with this particular, we're going to use these two functions to explore what we mean by this growth of functions theory. And so now let's take a look at our very first definition, G.1. Now, watch this, you guys. This is a little tricky. This is the definition, G1 is the definition of what we call the asymptotic upper bound. Now, we actually did upper bounds and lower bounds before with order relations, right? Remember, how the upper bounds were... Yeah, with the Hasse diagram. So it's a little bit, it has that flavor. It's the same kind of idea. Only this time, instead of doing it with individual individual elements. We're talking about continuous functions. Okay, so this is really actually not discrete because it's continuous. That's why this material isn't in the book. Okay, so because it's really not, strictly speaking, this is not a discrete math topic, but it's just so important that we're going to treat it. We're going to do it anyway. Okay, so now, so the definition of an asymptotic upper bound says this. Now let's see if we can understand what this says using our formal notation. For a given function g dot n. Now, big O of g dot n, you see up there in g.1, the way you write this, that's a, I don't know if you can tell, but that's a, or it's a big O and it's italicized, and the way we write this, handwrite this, is we put a little curl up on the top like this. And the way we say it is, everybody always pronounces it the same way. This is big O. All right. So big O, and it's a function, big O of g of n. Big O of g dot n, or big O of g of n. For a given function g of n, big O of g dot n, pronounced big O of g of n, is the set of functions. Now this is a little tricky. This represents a set. Notice that what we have by the definition is we have the curly brace. And furthermore, it's a set of what? It's a set of functions. Can you imagine that? It's a set of functions. Yeah? So there's a whole bunch of functions in there. Cubes, quadratics, log, whatever, just, just functions. Just a whole bunch of functions, okay? It's a set of whole bunch of functions. And it's a set of functions now, and then what is in the, what's in the range? It's one big existential. Are you with me? It's a set of functions such that there exists a what? A c and an n sub 0. We normally call this n naught, okay? So there exists a c and an n naught. And what do we know about the c and the n naught? They are both what? They're both positive, okay? So there exists a c and an n naught such that they're in the range both positive, such that for all, and now we have a nested, such that for all n, now what's the range of n? Greater than or equal to that n naught, okay, which is positive, okay. 0 is less than or equal to f dot n is less than or equal to c times g of n.
So what does that mean?
Yeah, that's a good question. And we are going to find out in detail what it means. Yeah. But so now let's do it. Let me show you. We'll do several examples, and I think you'll see after a while. All right? So here's our G.1 example. Actually, wait. Before we do this G.1 example, let me tell you something about notation. What we're going to prove, okay, actually, first thing, this is a set, right? A set of functions. Now, I'm going to state something here that we're going to do. And this has to do with notation. Okay? So we want to prove 2n squared plus 1 is an element of big O of n squared. This is what we're going to do. We're going to prove. In a minute, we're going to prove this. But now you notice how I wrote this. What is this big O? This big O is a what? No. It's a set of functions. And this is a particular function. And we want to prove that this function is in this set. Now, does everybody understand the types? Everybody understands what the type is. This is a set of functions. It's a set of functions such that there exists a positive c and n naught such that for all n greater than or equal to n naught, 0 is less than or equal to f dot n is less than c times g dot n. C times n squared in this case. Right? But now, And so, because this is a function and this is a set of functions, this makes sense. Now, unfortunately, there is a common notation. And the common notation is to not use is an element of. The common notation is 2n squared plus 1 equals big O of n squared. Now, that is weird. All right? And strictly speaking, is this a correct mathematical? No, because what do we know about equals? You have to have the same what? Type on both sides of the equals. Okay? But unfortunately, every book, I have never, you will never see the correct mathematical notation. You'll never see it written this way. You'll just see it. So what we have to do is we just have to like redefine what equals means when you're talking about big O. This really means is an element of, when this is a big O. All right? So it's not really equals.
It's not much harder to write the elements.
I know, but people don't do that. For some reason,
They had to redefine equals.
they had to yeah, you're right. They are overloading the meaning of equals now. In C, in Java, it's an assignment statement instead of being equals. It's just one of those things you have to put up with. Not really equals because of type conflict. But
Is this big O thing also like order?
yes, yeah, it's of order. Yeah, it's another way to say it. It's another way of saying this is 2n squared plus 1 is order n squared. Is order n squared. Yeah. Okay.
Where did you get the n squared from?
I just pulled it out of a hat. I'm going to show you that this is, and what I want to do is I want to prove this. Okay. So this big. Okay. So our.
You're showing that the multiplicative constants and the additive constants are.
Well, I'm going to show that this is bounded above by we're going to do the same thing for the 2n for the 15n plus 93. We'll do both of them. Okay. All right. So now, if you can prove, if you can prove that 2n squared plus 1 is, but we're going to use this because it's so common, we're just going to go with the flow here, equals big O of n squared. Then you have proved that 2n squared plus 1 is bounded above. Then you have proved that 2n squared plus 1 is bounded above. Is bounded above by n squared. Now let's see if we can, so the big O means bounded above. The way to remember this is, another word for O is over. So the bound is over the function. So now let's see if we can see, let's refer back up here to the chart, to the equation, all right, and see if we can see why this is bounded above. Look right here. We're going to prove that 2n squared plus 1 is big O of n squared. So our n squared over here is our what? Our n, this n squared is what? Is g. G dot n, right? So what we're saying is that, look at what over here. This says that, and this f is our what? Is 2n squared plus 1. So what we are saying is that this 2n squared plus 1 is less than or equal to a constant times the n squared. So that says that the n squared is above the 2n squared plus 1. Now do you see that that's the order that things are in?
Yeah.
All right. So in some sense, what this means, and this is very loose, if we say f dot n is big order of g dot n, it means roughly that in some sense f is less than or equal to g. Now this really doesn't make any sense, right? Because f is a function, well, yeah, because f is a function and g is a function. How can one function be less than another function?
Like G grows faster?
It means yes. It means g grows faster in the long run. Or the same.
If you have a certain constant on it. Like
Yeah.
Right now, in the example you have right there, f is greater than g. Any value.
Well, it depends on n.
No, because they're both n squared.
Well, but this is less. This means roughly less than or equal to. I mean, the point of it is it doesn't really make sense for one function to be less than or equal to another function, because at what point in n it might be less than it somewhere and greater than it somewhere else. So what do you mean? But roughly speaking, for large enough n.
Less than or equal.
Yeah, you see. So asymptotically, what we're saying is that whenever you say f dot n is big O of g dot n, you're saying that it's bounded above.
Okay.
You see, we're saying that g is an upper bound. What you have to do is you have to be able to prove this. So these are all proofs, okay? And the first thing we're going to do is we're going to prove that 5n, we're going to prove...
We're proving a definition?
No. We're proving a specific one. We're looking at specific examples, okay? Specific examples of functions. All right?
Oh, we actually can prove examples.
We can actually, yeah. Because whenever you write an algorithm, one of the things that you always do in data structures, every time you write an algorithm, you always want to investigate how does it grow. Because that tells you a whole lot about its performance. And we are really concerned, when we do software engineering, we're really concerned about performance. About how fast your programs execute for your customers. Yeah? Are you, okay? So let's do a couple of proofs. First, we're going to prove that 15n plus 93 is big O of n. Prove that 15n plus 93 equals big O of n. And really this means is an element of this set. All right? Now here's the way you always do this. You don't have to, I mean, what you do is you have to know this. What we have to prove is this. Yeah? So we must show, and you need to write this down every time, must show positive C and N naught such that 15n plus 93 is less than or equal to C times n. For n greater than or equal to n naught.
What is n naught?
Yeah, that's a good question. We have to come up with a number. It's a specific number. And if you look up here at G.1, then if n is greater than or equal to n naught, then as long as n is greater than n, we have to come up with a number n naught such that if n is greater than or equal to n naught, we can prove that f dot n is less than or equal to c times g dot n. You can kind of think of it as kind of like a sort of like a crossover point,
Right, yeah.
above which this bound holds. Are you with me?
That's exactly what it is, isn't it?
Yeah. And check this out, you guys. If you prove it for something bigger than the crossover point, that's good enough. And it doesn't have to be exactly the crossover point, but you know, as long as it's a constant, a positive constant. All right. Now,
We also choose the C.
well, we have to come up with a C and an N naught. Now, here's what's interesting about this proof technique. These proof techniques always follow the exact same pattern. What you do is you write down what you must show, and then you write down what the inequality is for n greater than or equal to n naught, and what we have to come up with this C and this n naught. And we always do it the same way every time. We always start with this. We always start with the left-hand side, with the function that we're trying to prove the bound on. And we do manipulations, and in the end, we get it to be greater than or equal to C times n, or C times whatever this function is, right? And in the course of doing this, we will actually come up with the C and an n naught. But you have to be creative. Now there's no, this is a little change of pace from a lot of our proofs, because we're dealing with inequalities here, and you have to be creative in how you, yeah, okay. So watch this. So here's the proof. So the way you do it is this. You say 15n plus 93. All right? Now, watch this. We want to get this eventually to be some constant times n. The problem is we have an n here, but we have a 93 here.
It's greater than 93.
Well, watch this. What do you say? I claim that this is less than or equal to 15n plus n. Now, I'm just pulling this out of the air. But now, wait a minute. Is this 15n plus 93 always less than or equal to 15n plus n?
So now our n naught is 93.
Provided that n is what? Provided that this n is what?
Greater.
When will this be greater than or equal to this?
93.
93.
As long as n itself is greater than or equal to 93. Greater than or equal to 93. This will be true, right? So here what we do is we do a proviso. Provided
And not.
n, no. Provided n is greater than or equal to 93.
Okay.
Are you with me? But now this equals, by math, what?
16n.
16n. I claim that this is equal to c. Now I'm trying to get this to c times n, right? I claim that this is equal to c times n.
Provided.
Well, provided what?
C is greater than
No. Equals.
C is 16.
C is 16. This is provided C equals 16. Are you with me? So therefore, what have we done? We have determined, because this is for n greater than or equal to n naught, so our n naught must be 93. So we have C equals 16, n naught equals 93, boom, and we're done. Because it says, look, let's go back here to our definition. It says there exists a C and an n naught. Well, we showed that they exist. Here they are. Here it is, 16 and 93. So therefore they exist. So therefore we've proved it. Are you with me?
Do you prove it the exact same time every time?
Well, I mean, the way we prove it, we have to show that there exists something. So the way you show that there exists is you actually go through and you mathematically, if C is 16 and n naught is 93, we know that this is less than or equal to this. Because we proved it here by mathematically. Are you with me? So we showed the existence. This is how we showed the existence. All right? So let's do another one here.
But do we do this, like, essentially the same steps every time?
Well, I mean, you have to be creative. I mean, sometimes the functions are a little tricky, and you have to be inventive with the way you come up with the... See, what was inventive about this is, you know, we changed this 93 to n because we knew we had to add this because we wanted that to be n, and, you know, I mean, you have to be... It's a little tricky, because you have to think. Okay, each case is separate. Let's prove that 2n squared plus 1 is big O of n squared. Prove that 2n squared plus 1 equals big O of n squared. Now, every time you do this, you have to write down what it is that you must show. Must show what? What do we always say?
Positive C.
Exactly. Positive C and n naught such that what? And then you always have to write down what it is that you, which is such that 2n squared plus 1. This time it has to be what? Less than or equal to what?
C times n squared.
C times n squared. Are you with me?
Yes.
C times n squared. For what? For what values of n?
N greater than or equal to n.
N greater than or equal to n naught. right? This doesn't mean N-O-T, this means N-O-U-G-H-T. I think that's how you spell it, not. The zero kind of not, okay. And where do we always start? We always start with this. Are you with me? So here we go, 2n squared plus 1. I maintain that now. Now, how should we manipulate this? Do you see how to manipulate this?
1 equals n squared.
Yeah, well, I claim that this is less than or equal to 2n squared plus, you're right. But the only, we want this to be n squared so we can combine it with this. Okay, but now, is this always true?
n greater than 1.
Yeah, if it's like a half,
And it's not.
then it's not, because a half times a half is a fourth, and this wouldn't be, right? So this
It's
is,
always true if it's integers.
Positive energy.
well, yeah, strictly positive. Yeah. Okay, so we'll say provided n
Greater than or
is greater than or equal to 1. Okay? And now this equals by math 3n squared, which equals provided that c equals 3, c times n squared. So this is less than or equal to c times n squared, right?
Yes.
So what values do we have? So c equals 3, n naught equals 1. Boom. We're done. We proved it. Is everybody good? Oh, okay. Actually, that point that I made about being in the set, that's G point 2. That's big O notation. F dot n equals big O of G dot n means function n is in the set. All right. Now, the same thing that we did for the upper bound, we can do for the lower bound. Only this time, instead of using the letter uppercase O, we use the Greek letter. What is that Greek? What is
Omega.
omega? So omega. All right. And the only difference with O and omega, big O and big omega, is what here. Let me see. What's going on here? What's the difference?
C times G of n is, you just swap the body at the final.
Yeah, so that has the effect of doing what? Of making the bound,
The function.
the function is bigger, so the bound is lower, right? So now this is a lower bound. So G3, G dot 3, what this says is that F dot n equals big omega. Oh, and the same thing with the notation. It's a set of functions, but you know, okay. So F dot n equals big omega of G dot n means roughly what? So now if this, instead of being bounded above, what's it bounded by?
F sub n is less than or equal to.
Well, the G, this is the bound.
Right, okay. Greater than or equal to.
Yeah. So it means roughly that F is greater than or equal to G. So this is a lower bound. F is bounded below by G. F is bounded below by G. All right? But now you prove it the exact same way. Only difference is you just switch the inequality, okay? So let's prove. Let's do a couple more examples. Let's prove that 15n plus 93 equals big omega of n. So anytime I ask you to prove one of these, you always start off, what do you always write? Must show.
Must show
Yeah, but you have to come up with values. Must show positive, C and not, such that, only this time we do such that what?
it's greater than.
Yeah, such that 15n plus 93
Greater than.
is greater than or equal to C times, and in this case, n. Okay?
See, it's a positive. I was like, can C be 0?
No, it's got to be positive, yeah. Okay.
You want the highest one that you can use, right?
Well, you know, usually that's what we, well, no, we want, well,
Kind of just like bounded in. Not, it doesn't have to be the exact highest, but like the greatest lower bound.
yeah. Well, it actually doesn't matter because it's asymptotic anyway.
Okay. It's just a lower bound.
Yeah. Okay, so so let's start off with this. Now this is kind of interesting. 15n plus 93.
Greater than or equal to.
It's greater than or equal to, now greater than or equal to, but now watch this. Watch, what do you think here? How can we,
Provided that n is less than or equal to 90.
no, wait, I don't think we do provided anything.
It's greater than or equal to C times.
Whoa. Yeah, I think this is greater than or equal to 15n.
Oh.
Now why is this? This is not provided anything, right?
Yeah. Okay.
It's because, why? Because 93 is positive.
92 is positive.
Okay? Because 93 is positive. So if 15 plus n plus a positive is surely greater than or equal to 15n, right?
Absolutely.
Is positive. So this isn't provided anything. Okay? And now what does this equal?
C times n provided that.
Yeah,
15.
provided C equals 15, this equals C times n, which is what we were trying to prove, right? C times n. We're trying to prove this is greater than or equal to C times this. Okay, so now what? But
So C equals
so and furthermore, any n will do. Okay? So any n will do.
and not, right?
Yeah, any n not will do. So pick one. Just pick one. Just pick a positive. What's the easiest positive one? So any n not will do.
Doesn't it have to be less than 93?
10.
No. Well, how about 1? Say 1. Okay.
Why
So we have C equals 15, n naught equals 1, and we're done because that it exists.
Is this going to be something I don't like? Because if we did pick 100, would it matter?
It wouldn't matter.
Why not?
If n was 100, then
It doesn't.
the first step wouldn't work.
Yeah, it would because it doesn't depend on, because 93 is positive no matter what n naught you pick.
Oh, you're right.
93 is
You're right.
positive no matter which n naught you pick. I mean, that's true regardless. Any n, I mean, it didn't even enter in.
Yeah, it isn't.
You see it doesn't even enter in because, yeah, are you with me?
Yes.
Okay. So that's interesting, huh? Now let's prove that, let's do another one. Let's prove that 2n squared plus 1, 2n squared plus 1 equals big omega of n squared. All right. So what must we show?
2n squared plus 1.
No, positive what?
Positive c and n squared.
Positive c and n naught, not n squared. Are we good? Okay. With what?
Not n not squared? Oh,
No.
well.
This is n naught. Yeah.
So 2n squared plus
2n squared plus 1 is what?
1
Greater than or equal to
n squared.
c times n squared. Okay, so now you have all that? Okay, so that's the c. This is the one that it's bounded below. This is the lower bound. right? So C times that lower bound, okay? This is similar to the other one. So here's the proof. So we start with what? 2n squared plus 1 is greater than or equal to what? Just 2n squared. Because why? Because 1 is positive. Because 1 is positive, yeah. So if you drop something positive, that's got to be greater than or equal to this. But this equals, provided provided C equals 2, C times n squared. And here again, any n will do. Any n naught will work. Say 1. And so we have C equals 2, n naught equals 1, and we proved it. Are we good? Okay, now there's one more. We did a big O, and we did a big omega, right? And now the next one on our list of definitions here is big theta. Now what does big theta say? F dot n is big theta of G dot n if and only if what?
Function
F dot n. Yeah, so now what in the world does this mean? This, because here, if F dot n is big O of G dot n, that means G dot n must be what kind of a bound? Upper bound or lower bound? Is G dot n an upper bound or a lower? Remember, O means over.
Yeah, it's upper.
So this means G dot n is an upper bound. But this means G dot n is also a what?
A lower bound.
A lower bound. Holy moly. How could it be both an upper bound and a lower bound? Well, we actually just did both of them. Okay? So G.5, here G.5, whenever you say F dot n equals, now the way you write theta is you put a big circle with a uppercase H in it. That's kind of how you write it, that's how you handwrite it, okay? Big theta of G dot n means roughly what? Well, if big omega meant that G dot n was what? Above it, and big omega meant that it was below it. Well, if it's both, then what does that mean roughly? They're kind of like equal. They're not equal everywhere. In fact, they're probably not equal anywhere. But still, they grow the same way. The upper bound and lower bound, you see, means roughly F equals G. That's kind of a way to think of it. Okay? And the two examples that we have, we've already done. In other words, we just proved that we just proved that 15n plus 93 equals big theta of n. And another example that we just proved that 2n squared plus 1 is big theta of n squared. Because we proved both ways. Now, I want to actually hasten to add that this definition of big theta is really not quite the way most books do it. The way most books do it is, in the way we're doing it, G.6 is a theorem and G.5 is a definition.
Yeah, but it's different.
Most books do it the other way around. I don't know why, because this is a whole lot easier to understand. But if you look at G.6, big theta of G.n is the set of functions f dot n such that there exists, now look, this is more complicated, because what does it say? There exists a what? A C1 and a C2. So there's two C's and one n naught. And the C's are greater than 0 and the n naught is greater than 0.
It's basically doing both the big O and the big O.
It's basically doing both the big O. Yeah, it's doing the C1 times Gn is less than or equal to f dot n is less than or equal to C2 times G dot n. So it's doing it all in one humongous monolithic thing. But I mean, you know, but then to prove this directly, then you got to have just one end knot and a C.
It's easier to understand G6 and C6.
Yeah. So anyway, I prefer to flip it. Because you can do it either. I mean, either this could be a definition, and in those books, this is a definition and this is a theorem. They always do this as a theorem. So, you know.
So you turn them all into giant set quantifications.
Yeah, but anyway.
Can you prove G6
Oh, absolutely.
from G5?
Yeah.
That's what you're supposed to do?
Yeah. In fact, it's easy to see how you would do it, because what you do is the N naught would just be the greater. You know, you'd have the C1 and the C2. Well, the N naught would be the N. You'd have here you'd have a C and an N naught for this, and here you'd have another C and an N naught.
That's true.
So the N naught for the combined would just be the greater of the two, because if it's greater than or equal to the first, it's greater than or equal to the second. So, anyway. All right. I want to, well, I think we'll finish up. We'll finish this up. Actually, we'll easily finish it up next time. All right? So we'll see you on Thursday. We'll finish this up and we'll start theory of integers. Okay.